Yeah, as we were discussing this relationship between, it's a digression, in a short digression, but it's important. See, when you drew the root locus, no, in the S plane, when, and then suppose you had poles in these locations, sort of, right? Um, and and then they moved in a particular way, maybe something like that or whatever. And the root locus meant that, as you said, when you change a particular physical parameter of the system, how the poles are moving. Now these poles represent, now and then you also said that they are symmetric about the x-axis, which meant that this and this, they belong to a single second order system, because they are the complex roots, right? So that means any system you can break into multiple either first order or second order systems, because any polynomial can be broken into these things, isn't it? Either you go to a first order thing, nth degree polynomial if you take, you can get up to that level, either second order or first order. Cubic also can be broken like that. So if you consider complex roots, so that means, and then you can do a partial fraction of that. So partial fraction means it tells you that they are separate systems. Now you are seeing the combined effect of all those first order or second order systems. So any such pairs which are complex pairs are talking about one of those second order system which is part of the whole system, and whatever is lying on the real axis, it is like a first order system. So they are all together to make your whole system, right? So it's not that this is one system, this is another system, it's not that. This whole bunch as a combination is your system, right? And the movements of these poles on these paths tell you that if you move or if you change the knob of that particular parameter, in what direction they move. But then the major visualization should come from this picture, that remember we talked about the impulse response, right? So every location here on this complex plane has got its characteristic impulse response, right? For example, if you are here, so if you give an impulse, it will just die out like this. I'll do like say like this, I'll do, okay. Now if you come here, the same response will be faster. That's the meaning. If you go farther and farther from the origin, it will be faster and faster dying system. And if you come here, it will be even slower, like that. But they will die. So that means if you have a component of your system on the real axis, its response to an impulse is something like this. Now when you come to locations like here, they mean that you have sinusoids. Now here, if you go up and up, so here if I do the same thing, I'll get a picture something like maybe like that, okay. But if I go up, the frequency is changing. If I go here, it will even be faster, like that. And if I go to left of this, the dying rate will increase. So the same thing, if I draw it here, this frequency will remain same, but the dying rate will maybe, this is what you are seeing that. So that is how the complex plane or represents in terms of a pole being somewhere. And then you are thinking about if your system is made up of so many subsystems. Now and then once you do the partial fraction, you will get the coefficient. So that is the weightage of every system, how much weightage every system has got. So then once you give an impulse, each of these subsystems will behave on their own. They are transparent to each other again, because we are talking about linear systems. So this is one system, this is another system, this is another system.
But how do we know the weightage of those systems?
Once you see, when you had a single denominator, you did the partial fraction. The coefficient of the partial fraction are the.
So, but how do we see that here?
Here you don't see that. Here you don't see that. When you multiply that, you will multiply that. Okay. Here you are just seeing that. But see, those coefficients are not that important as the relative locations are. Okay. If something is very close to the imaginary axis, obviously that will remain in a steady state, because everything else will die out. Now this guy here, this represents a subsystem, but you think about its dying rate. It's too fast, right? Almost within fraction of second it will die out. Its effect won't be there, but this guy will stay alive for a long time, and in the steady state, if you see, after a long time, its effect will not be there, its effect only will be there. So those are more important than those things, those coefficients. And yeah, so what I was saying is, once you give an impulse, all these subsystems will behave according to their own property, or I'll say according to their own location. Wherever they are, they will behave according to their location, because location now defines their behavior. And when you change the knobs to change their locations, you are basically changing their impulse responses, because location changing, behavior changing, combined behavior changing. So that's how the whole thing is, and you just sum up all the impulse behaviors, you will get the impulse behavior of the thing. And once you know the impulse behavior, you know the full to any what do you call forcing function, you know how to do that, right? By convolution. Once you know the impulse response of the whole system, you can find out now how the system will behave to a arbitrary forcing function, because any arbitrary forcing function can now be broken into impulses of different strengths, and then you sum them up to get the total response of the system to any arbitrary random forcing function. So that's again, see, so the story of your root locus and the story which we studied, they are exactly the same thing. So that was about root locus. In the Bore diagram, that was nothing but your what you did, the frequency response. That was for frequency response, Bore diagram. In that you always drew this side as frequency, right? Log scale. You did that log scale, that's a separate story, but this side was frequency. And the same thing what we studied here, in steady state, after a long time if you wait, for a given harmonic response or given harmonic excitation, how the system will behave. So your Bore diagram always had two components, right? The magnitude and the phase, isn't it? So the same thing, how the magnitude changes with respect to frequency. If you had something like this, so in this zone the frequency is changing, but the magnitude ratio is not changing, right? So that the whole story about the Bore. Even in Bore diagram you had this kind of drawings, right, for second order systems, which may told you the same thing, that as you go to the natural frequency, if you give the excitation, the amplitude will be very high. Only thing was that because you took the log here, it started from 0, because when the amplitude ratio is 1, that means when you are exciting it very slowly, है ना? If you take a spring mass damper system, you excite it with very slow harmonic motion, as if it's a DC value. So the amplitudes will be exactly same. Now if they are exactly same, if you take log of that, it will become 0. So that means at 0 dB you are drawing that. And you also had the phase diagram. Always Bode diagram has two parts, right? So the phase is between that, the excitation and the response, which we have discussed. And anywhere in any linear system you have to think in this term. And the same thing you, when you went into state space, the whole concept of I think last time we studied, no, in terms of the mode shapes, you try to see in terms of mode shapes, and the mode shapes are the eigenvalues of your transfer function or state space matrix, and your eigenvectors were the modes sort of thing. And in that perspective you try to analyze the system. Exactly the same things. And the Nyquist basically is about stability from the perspective of not from magnitude but from the phase information. Because once you integrate something in contour integration, no, the phase changes in a particular way because it's a multi-valued function. So it behaves in a particular way, and that information of integration of complex valued function in arguments, so that was used to talk about the stability of the system in the Nyquist. So that's the whole thing. So root locus, Bode, Nyquist and state space, everything is exactly up to this point whatever we have discussed. They are very closely correlated. Okay. Okay, so we will stop this digression and we will start today's discussion.